Hello everyone, my name is Bogdan Kolinic, and I'm going to talk about our paper on disparate vulnerability to membership inference attacks. So what are membership inference attacks? These are attacks against privacy of machine learning or statistical models in which an adversary aims to learn for a given record X whether this record was part of the training dataset or not. Because machine learning models are a bit like parrots, they can memorize what they have seen in the training data. By querying and inspecting the model in different ways, an adversary can get a non-trivial advantage at identifying if a record was used in training or not. Researchers have noticed that different records can be differently vulnerable to membership inference attacks. This observation comes in two forms. First, some works have pointed out that there could be outlier records that are more vulnerable than others. Second, other researchers have noticed that whole semantically related subgroups of data can have higher vulnerability than other groups. In our work, we study the latter aspect, disparate vulnerability to membership inference across data population subgroups. Studying this form of disparate vulnerability is important, among all else, from the legal point of view. Legal scholars have argued that membership inference attacks are a good tool for auditing machine learning and statistical models for their privacy leakage. For example, under GDPR, the scholars have argued that if a model is vulnerable to membership inference, the model should be considered personal data and thus treated in a special way. The issue that can come up here is privacy washing through the usage of average metrics. If we only look at average vulnerability across the population, we might miss situations as before, and we might miss some records that have higher vulnerability. If these records are semantically disconnected outliers, this vulnerability is easy to dismiss as acceptable risk. If these records, however, all belong to a socially salient group, this is much more concerning, and for example, privacy auditors might be accountable to those groups. This is why being able to reason about and audit disparate vulnerability, specifically across population subgroups, is important. In this talk, I will discuss three aspects of our paper. First, regardless of any disparity considerations, we aim to answer the question when exactly the models are vulnerable to membership inference. Second, we extend this insight to disparate vulnerability. And then third and finally, I will talk about how we should measure disparate vulnerability. So let's start with figuring out when exactly the models are vulnerable to membership inference. It is intuitive and well known that overfitting or lack of generalization is a sufficient condition for a model to be vulnerable to membership inference. Generalization is characterized by this gap between the average loss on the training data on the left here and the average loss on the test data on the right. Indeed, if the model has much lower error on its training data, an adversary can recognize training examples by looking at the loss. There is a recent notion that generalizes generalization, pun intended, called distributional generalization. If classical generalization only considers the average of the distribution of loss, distributional generalization uses a probabilistic metric between train and test distributions. Specifically, we use total variation distance. Moreover, not only we'll look at the loss, but any other numeric property of the model, here denoted as phi. In this work, we analyze the worst-case vulnerability to membership inference attacks that use a certain feature phi to conduct an attack. Most commonly, this feature is a loss, but any other numeric function of the model and an example could work. We formalize the worst-case vulnerability as the best possible normalized attack accuracy in a standard formalism by Yam and colleagues. We show that this worst-case vulnerability is exactly equal to the distribution generalization gap. So if poor classical generalization is a sufficient condition for vulnerability, the necessary and sufficient condition is poor distributional generalization. Next, we extend this insight to disparate vulnerability. And for this, we introduce a special subgroup-aware adversary. If we can conduct an attack using certain features phi, for example, losses before, then a subgroup-aware version of that attack would additionally use the subgroup to which an example belongs. We showed that the worst-case vulnerability with subgroup-aware adversary is always equal or higher than the worst-case vulnerability to an adversary that does not use subgroup information, so using that is always beneficial to the adversary in the worst case. We use this insight as a tool to connect subgroup vulnerability and distribution generalization. We can look at a subgroup-specific version of distribution generalization, which, as before, is the distance between train and test distributions, but this time the distributions are conditional on the subgroup, and as a technicality on the fact that the trained data contains at least one example of the subgroup. Then we can show that the worst-case vulnerability to a subgroup-aware adversary, denoted as V sub z, is equal to subgroup-specific distribution generalization gap. Because subgroup where adversary always causes higher vulnerability in the worst case, subgroup vulnerability for any other adversary is upper bounded by this distributional generalization gap as well. And by the way, disparate vulnerability is simply the difference between the subgroup vulnerabilities for two subgroups. So it is sufficient to study subgroup vulnerability as an object. This concludes the theoretical part of the talk, and I would like to now discuss some practical considerations about measuring disparate vulnerability. And I would like to start with a curious observation that we had. We tried to measure disparity in subgroup vulnerability between two synthetic groups. We fixed the size of one majority group and varied the size of the minority group. And then we ran some membership inference attacks in the setup. And what is interesting, the models that we were attacking were kind of dummy models. At the training stage, the training algorithm of these models would take as input the training data set and just throw it away and return the constant model every time. So the models that we were attacking were independent of the data. And we did this strange experiment to verify that vulnerability and disparity in vulnerability for all such models would be zero, right? Because the models have not really touched or used the data, they cannot be vulnerable to membership inference. We ran three kinds of attacks. I will talk about them more in a bit. And to our surprise, whereas for some attacks, such as average loss threshold attack and shadow model attack, the disparity was around zero, which is what we expected. For another attack, which is a much more powerful one, the optimal loss threshold, we saw statistically significant non-zero disparity, and this should not happen because the models that we attack have not used any data. There can be neither any membership inference advantage nor any disparities in this advantage. To understand what's happening here, why this is happening, we first have to discuss different approaches to model an adversary's knowledge in membership inference. First approach, the shadow model or reference model approach. Here, the adversary is assumed to know the data distribution and the target model training algorithm. With this information, the adversary can reproduce some models that look kind of like the target model, learn an attack on them, and then deploy the attack against the target. In the other approach, which I'm going to call worst case here, the adversary directly has access to some information about the target model's properties on the training data. For example, in one such attacks, the adversary obtains the average loss on the training data. In other attacks that we call optimal threshold, the adversary gets the threshold on the loss that is actually carefully chosen to distinguish train loss values from test values. The danger of this approach, of course, is that it goes a bit against the goal of membership inference, because in membership inference, the adversary wants to learn something about the training data, yet here the adversary already starts with some non-trivial information about that training data. However, this enables us to estimate worst-case vulnerability, which is a standard practice in security. Unfortunately, it is inherently problematic for estimating specifically disparity in vulnerability. This is because we want the membership inference to exploit the model's memorization behavior, exploit the fact that the model behaves differently on training examples and test examples. With the worst-case approach, however, because the adversary has access to non-trivial information about the training data of the target model, there is another source of information beyond model memorization that we do not want to capture. And it's the sampling bias, which is the fact that the finite training data set is always going to be somewhat different from the actual data distribution. And this is what also enables the adversary to tell training examples from test examples. This bias depends on the size of data, and it vanishes pretty rapidly, except when we are deploying our attacks on small subgroups of data. For example, the subgroup of size 50 is something that we saw in the literature, and the sampling bias definitely has an effect at this scale, as we see in the plot. Thus, if we measure disparity between two subgroups using the worst-case approach, we will always see disparity if the subgroups differ in size. So the measurement just becomes meaningless and also misleading. To test attacks for this unwanted property, we proposed the so-called null model bias test, which is exactly what we did before. Evaluate attacks against data-independent models. And if we see any non-zero vulnerability, then the measurement of vulnerability is biased and should not in general be used to measure disparate vulnerability. Should not be used to measure regular vulnerability, but as long as the size of the data is big, the bias is going to be negligible. So to be safe, one should only use attacks in which the adversary cannot access anything about the training data when building the attack. As an exception, our experiments showed that the average loss threshold attack was not biased in practice, probably because just a single average loss value is not sufficient to bias the results. In the paper, we also discuss some other considerations one should take when measuring disparate vulnerability. For example, because the groups could be small, we want to use statistical tests to make sure that the observed disparity is not a fluke. We also apply methods to verify that we can detect disparate vulnerability in realistic settings, and we do that with high degree of statistical significance. Finally, we'll also discuss how one can prevent disparate vulnerability. We show that differential privacy bounds it, and that some algorithmic fairness interventions can reduce it, but only for specific adversarial models, so they're not a valid defense. To sum up in this talk, I briefly outlined the following aspects of our paper. First, we have argued from a legal standpoint that it is important to evaluate disparate vulnerability across demographic subgroups to avoid privacy washing through aggregate metrics. On the theoretical side, the worst-case vulnerability to membership inference is characterized by distributional generalization. So we show that if poor standard generalization is a sufficient condition for membership inference vulnerability, poor distributional generalization is necessary and sufficient. And then disparate vulnerability is bounded by difference in subgroup level distributional generalization. Finally, on the practical side, we argue that one should not use attacks that have non-trivial access to the training data to measure disparate vulnerability. Something that we have in the paper, but not much in the talk, is that we should use statistical procedures to establish statistical significance, and we discussed various mitigation strategies against disparate vulnerability. This concludes the talk. Please check the paper for more details, and thank you for your attention.